Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface and Oracle's online documentation. Chapter 4, we are looking at the functions inside the JNI.h or JNI environment pointer, which is the object that we work with, right? So interface function table, each function is accessible at a fixed offset through the JNI environment argument, right? The JNI environment type is a pointer to a structure storing all JNI function pointers. It is defined as follows. So JNI environment is basically, I always call it JVM. That's the interface that we work with. That's the interface that does the stuff for us. If we want to talk to the JVM at runtime, we use this JNI environment object. And it's a struct and holds the function pointers of the JNI. So type def const struct JNI native interface pointer JNI inv. So JNI inv JNI environment is a type def of a const struct that is a pointer. So it's a type def of a pointer to a struct that is a constant, right? So the pointer is not constant, but this this struct is a constant. The VM initializes the function table as shown by the following code example. Note that the first 3 entries are reserved for future compatibility with COM. In addition, we reserve a number of additional null entries near the beginning of the function table so that, for example, a future class-related JNI operation can be added after find class rather than at the end of the table. So they're reserving some null space here so that they can use them for in the future. So const struct JNI native interface, and it's inline definition. So null. So we know that null is just 0, and depending on the platform, it's either a 0 integer or 0 line, right? And we said that in modern C++, if you want to say a pointer is null, instead of using this null, which is a C macro, we use the null pointer keyword in C++. But they put null here, null 0. Let's assume that it's a long, so this becomes 8 byte, right? A 0 long is a long integer is 8 bytes or 64 bits. 8 byte offset, and this is a struct, and we know that classes and structs in C++ have a flat layout, right? They don't have any header, anything. This is the exact flat layout in the memory. So 8 byte, get version, it's a function pointer. Define class, find class, it searches the class path from reflected method, from reflected field to reflected method. Get superclass is assignable to reflected field. So these are all the functions, and then call byte method, and these are actually function pointers, right? So these are all callable, so we can call them because these are pointing to the functions. Static ones, string ones, array ones, working with arrays, register natives, unregistered natives, get Java VM, get a string UTF, new weak global ref. So these are the primitive refs, critical access to arrays, and then new direct byte buffer, get direct byte at buffer address, get direct buffer capacity, get object ref type. So version information. So get version JNI environment pointer returns the version of the native method interface. And we've seen some versions here when we looked at the JNI unload. We saw that in the JNI unload, we saw that there are some, so when we use JNI unload, its return type is an integer, which is returning the version of the Java is being used. And there are some predefined macros in the JNI.h header file, JNI version 1.4, JNI version 1.6, JNI version 1.8. So we can also use this get version, right? To and pass in the JNI environment pointer, or basically our JVM, right? I always define the JNI environment pointer as my JVM that I can talk to and work with, and then it gives us the version, returns the version of the native method interface, linkage index 4 in the JNI interface function table. And again, the JNI interface function table is basically a flat memory, right? Index 4, and these are all pointers, right? These are all function pointers. This is all of these are callables. These are function pointers, and a pointer is 8 bytes on a 64-bit platform. So the first 8 bytes, or the first index, is 8 byte, 8 byte, 8 byte, 8 byte. So this is a flat, this struct is a flat memory layout, right, of 8 byte entries, which are addresses or pointers. Index 0, index 1, index 2, index 3, these are nulls, right? And index 4 is the get version. So it's index 4 in the JNI environment interface pointer, right? Parameters, environment, so this takes the pointer, JNI environment pointer, and then it takes the JNI interface pointer and returns the major version number in the higher 16 bits and the minor version number in the lower 16 bit, and it returns a JInt, and JInt is guaranteed to be 32 bit. So it says that on a JDK 1.1, 1.2, 1.4, and 1.6. So since JDK 1.6, JNI version 1.6, right? So in JDK 1.8, if you open up the JNI environment pointer, you have only 3 versions: 1.4, 1.6, 1.8. And basically, they decided to only keep the last 3 versions, basically, or the last 2 versions, including the current one, right? So get version. So the first 16 bits or 4 bytes returns a basically so the 2 bytes, right? The higher 2 bytes or the higher 16 bits is the major version, and the lower 16 bits is the minor version of Java, right? 1 means so this is 1 0, and then this is 1 0, right? Each one of these zeros is 4 bits. These are hex, so 2 bytes, 2 bytes, 4 bytes. So on JDK 1.6 is 1 and 6, right? And if you want to get this, you can read this, and then basically what happens is you mask the first 2 bytes, and then mask the second 2 bytes and shift it to the right. That's how we can get this information from a simple integer in hex representation. So constants, all right, so get version returns these numbers, right? And these are also predefined macros in JNI.h, the version numbers. Constants, since JDK 1.2, they added these constants, JNI version 1.1, JNI version 1.2, and the error codes define JNI E detached, JNI E version, right? JNI version error version, and thread detached from the VM. So these are the macros, and in JDK 1.4 they added the JNI version 1.4. In JDK 1.6 they added JNI version 1.6, and of course in JDK 1.8 they added JNI version 1.8. So class operations, define class. J class, define class, basically it's a function. It takes the environment pointer, and again in C++ we don't pass the environment pointer, right? Which these are redefined in the C++ version, so that we don't need to have this indirection. Again, we do not need to pass the JNI environment pointer as the first argument. Const, this is the name of the class. J object loader, we have to specify its class loader. Const J byte pointer a buffer, and then J size buffer length, right? So loads a class from a buffer or raw class data. So if you want to load a class, the buffer containing the raw class data is not referenced by the VM after the define class call returns, and it may be discarded if desired. So this is equivalent of getting a class loader and loading a class object, because class object is just binaries. Those binaries are basically equivalent to this byte buffer. Index 5 in the JNI interface function. By the way, what this indexing means, you can get the JVM. It's a pointer, right? And it's pointer to the first entry. So if I say JVM plus 5, it actually gives me a function pointer, and if I say JVM, this JNI environment pointer is the JVM. If I say JVM plus 5, It starts from the first entry, first index in the JVM, in the JNI environment pointer, and then goes to the fifth index, and that's pointing to the function pointer, which is defined class. So if I dereference, and then I can use the call label on it, because a function pointer is call label. So basically I can get it. Parameters, so define class environment, JNI environment pointer, name, the name of the class or interface to be defined. The string is encoded in modified UTF-8. We discussed this before. Backward compatible with ASCII. Loader, a class loader assigned to the defined class. Buffer containing the .class file data. Buffer length. So if we want to manually load a class, we can use this defined class to load it. Returns a Java class object, or null if an object, if a error. Okay, so it returns a J class. Throws a class format error, class circularity error. So class format error if the class data does not specify a valid class. Class circularity error if a class or interface would be its own superclass or super interface. Out of memory error if the system runs out of memory. Security exception if the caller attempts to define a class in the Java package tree. Find class, this is the most famous one that we've always been using. This finds a class on the class path and automatically loads it in the memory and gives us a handle or a pointer to that in Java heap. So it returns the J class. So J class, find class, and again, in C++ we don't have this in direction, so we don't pass the JNI environment pointer again. Const pointer name, that's just the name of the class. It's a fully qualified name of the class, which is on the class, which should be on the class path, and that's a C style string. So in JDK 1.1, this function loads a locally defined class. It searches the directories and zip files specified by the class path. So it can also load from a jar, and we've seen this. So jar in C++. Okay, so jar, let's see if we can find it. Using jar files in C++, and we said that it's the same story. So basically, I say I have a jar on my class path, and we know that in Java, the Java compiler checks if we import something, it's actually that class is on the class path or not. So the jar should be added to the class path at compile time. But in C++, it's all about the JVM, right? It's all about the runtime. So we tell JVM to find the class on the class path, and all JVM doesn't, basically we just have to make sure that this class is available on the class path, and it's the package / the class name. It gives us a J class. If I want to call a method inside that class in that jar file, it's very similar. We just get the J class handle, J method ID, and then call the method, static method or non-static method. Okay. Since JDK 2 SDK release 1.2, the Java security model allows non-system classes to load and call native methods. Find class locates the class loader associated with the current native method, that is the class loader of the class that declared the native method. If the native method belongs to a system class, no class loader will be involved. Otherwise, the proper class loader will be invoked to load and link the name class, right? So, I mean, if the class has not been loaded, first the class loader is identified, and then it loads the class, and then gives us a J class handle to that class in the Java memory. Since Java 2, when find class is called through the invocation interface, there is no current native method or its associated class loader in that. So again, invocation interface is when we are launching a Java virtual machine from a C++ application, from inside a C++ application. And again, this is not something that we typically do. In that case, the result of class loader dot get system class loader is used. This is the class loader the virtual machine creates for applications and is able to locate classes listed in java.class.path property. And again, we have three class loaders: the bootstrap class loader, the extension class loader, and then the system class loader. And the system class loader, its job is to load the classes that are on the class path. They're not part of the JDK or the extension libraries. The name argument is a fully qualified class name as a C style string or an array type signature, right? For example, the fully qualified class name of a java.lang.string, and again, inside the JVM there is no dot separator, it's always forward slash. So package slash another package slash the Java name, and again, this is not the signature, this is the full qualified name, so it doesn't basically it doesn't start with L and end with semicolon, right? It's not the signature of the string object, it's just its fully qualified name, it's class path. The array type signature of the array class Java lang object array is L, so L Java / lang object semicolon, that's the signature of the object, and a square bracket L. So if we want to load int array in the memory, then we have to, the signature of the int array class is a square bracket for array and capital I, right? If we want to load an object array, it's a square bracket for array, but then we have to add the L semicolon, right? Linkage index 6 in the JNI environment function table. Parameters, again, in C++ interface we don't have this indirection, we don't have this environment. Name, a fully qualified class name, that is a package name delimited by forward slash. Again, there is no dot. The delimiter in the Java path is forward slash inside the JVM, right? Followed by the class name. If the name begins with a square bracket, it means it's an array signature character. It returns an array class, int array, whatever. The string is encoded in modified UTF-8. Again, if I want to work with an int array, first I have to get a J class of that type, which is int array. And the way we do it, we say define a JVM find class, and then in the double quotation in the string we just say a square bracket capital I, which means gives me a handle, a J class to the meta information of an int array. It's a built-in type, right? The string is encoded in modified UTF-8. Returns a class object, a J class, from a fully qualified name, or null if the class cannot be found. So it doesn't throw any C++ exception or whatever, it just returns a null. And again, null or null pointer is the same because J class, all these objects are just pointers, type defs of pointer types. Throws class format exception, and these are the Java errors, right? Class format error, class circularity error, no class def error, and then no class def found error if no definition for requested class or interface can be found, out of memory error, which is obvious. Get superclass gives us a J class of the superclass of a Java type, right? And we don't pass the J object, we pass a J class, right? Because we want to get a J class handle of this particular class. And in Java, each class can have only one superclass, so that's no problem. If class represents any class or other than the class object, only the object class doesn't have any superclass, then this function returns the object that represents the superclass of the class specified by this J class argument. If class specifies a class object, Java lang object, or class represents an interface, this function returns null. So interfaces don't have a superclass. The Java lang object also doesn't have a superclass. Index 10 in the JNI environment interface function table. Parameters, and again, we don't have this environment in C++ because we don't have this indirection. Class, a Java class object. So we pass in a J class to this get superclass because we're just talking about the meta informations, not the actual J object. Returns the superclass of the class represented by class, or a null pointer or null. Null macro or null pointer, their equivalent. Is assignable from, JBoolean is assignable from, so J class class 1, J class class 2, and this returns a JBoolean, determines whether an object class 1 can be safely cast to class 2. So this is a check cast, checks the cast, right? And obviously we expect it to return it returns a JBoolean, and we said that JBoolean is compatible with Boolean, right? With the bool type in C++. So because bool type is just an integer, 0 or 1, 0 or non-zero, and JBoolean is unsigned char, 1 byte unsigned integer, which again is compatible with integer types, bool type. But then we can check against the macros JNI true and JNI false. These are defined in JNI.h header file, and I believe JNI true is just 1 and JNI false is 0. So checks if class 1 can be basically checks whether an object of class 1, and again we're working with the meta information of the classes, because casting is something related to the class itself, if the cast is possible or not. Determines whether an object of class 1, the first argument, can be safely cast to class 2. Linkage index 11, class 1 the first class argument, class 2 the second class argument, and again it checks if the class 1 can be casted to class 2. Returns the JNI true if either of the following is true. The first and second class arguments refer to the same Java class. I mean, in terms of casting in Java, we know that a class can be casted to itself, a class can be casted to its subclasses. The first class is a subclass of the second class, right? So a subclass can be cast to its superclass, right? The first class has the second class as one of its interfaces, and obviously these are all polymorphism, right? If the first class is a subclass of the second class, then it can be casted to the superclass, that's fine. The first class has the second class as one of its interfaces, and again it can be safely casted. Obviously a superclass cannot be cast to any of its subclasses because it's not possible. Exceptions, throw, this just throws a Throwable. If we have a handle to a pointer to any Java exception, we can just throw it or re-throw it again. Throw is just equivalent in Java, we write throw new whatever, or if we have a reference to an exception, we just throw it again. It's exactly the same here. Causes a Java lang throwable object to be thrown. Linkage index 13, and then parameters object a Java lang throwable object, and returns 0 on success, a negative value on failure. So these all return some error code, whether there was a success or failure. 0 here means success, and negative value on failure. Throws and then throws a Java lang throwable object, right? Throw new, this throws a new exception, right, of type whatever J class we specify. So the difference between throw and throws here is that between throw and throw new is that throw basically just throws any object handle that we have to have a reference to the object. But throw new, it just takes a C style string as the message, and then we tell it which class this exception should be. Is it illegal argument exception or whatever? So again, the business here is the same. We get the meta information of the class that we want to work with, so that JVM understands what class we are referring to, and then the message. And this basically equivalent to saying, for example, if I have illegal argument exception, it's equivalent to say in Java new illegal argument exception, and in the constructor we pass in the message. Constructs an exception object from the specified class with the message specified by message, and causes that exception to be thrown. Linkage index 14 in the JNI interface function pointer. And we've seen how to handle the exceptions many times. We had an in-depth look at the exceptions in JNI. 4 functions: exception occurred, describe, exception clear, and exception check. Alright, so linkage index 14, class, a subclass of Java lang throwable. Message, the message used to construct the Java lang throwable object. The string is encoded in modified UTF-8. It's a C style string. Returns, throws the newly constructed throwable object. Exception occurred, it returns a reference to the exception object. Determines if an exception is being thrown. If it returns null, obviously it means no exception was thrown. If it returns a null value, a valid pointer, it means there is an exception on the Java stack, and this is a reference to it. The exception stays being thrown until either the native code calls exception clear for handling the exception, or the Java code handles the exception. Because if we don't handle it, as soon as we return from native call to the Java, then this exception object is still on top of the Java stack. So either we have to have some sort of try catch block in Java. Otherwise, as soon as the JVM returns back from the C++ code to Java code, it freaks out and jumps out of the method and then starts doing the stack unwinding. So linkage index 15 and then returns the exception object that is currently in the process of being thrown, or null if no exception is currently being thrown. And obviously a better way of checking if there is an actual exception, we can use exception check. Exception describe, this just prints the exception on the stack, prints the stack trace on the terminal, prints an exception and a back trace of the stack to a system error reporting channel such as std error. This is a convenience routine provided for debugging. So exception describe just prints the stack trace on the console or whatever error reporting channel the environment has. Index 16, exception clears any exception that is currently being thrown. If no exception is currently being thrown, this routine has no effect. Index 17, and then fatal error. Fatal error is very obvious. It takes a message and the JVM obviously terminates, raises a fatal error and does not expect the JVM to recover. This function does not return, so the JVM terminates. Linkage index 18, and then takes a message, a CS style const-char pointer. The string is encoded in modified UTF-8. Exception check. We introduce a convenience function to check for pending exceptions without creating a local reference to the exception object. JBoolean exception check returns JNI true when there is a pending exception, otherwise returns JNI false. And again, we can just directly put it in the if block because JBoolean is compatible with bool type in the conditions, but we can also compare it against JNI true and JNI false. Index 228 in the JNI interface table. Global and local references. Global references, new global reference, JObject new global reference. It gets a JObject reference and gives us a new reference. Creates a new global reference to the object referred by the object argument. The object argument may be a global or local reference. Global reference must be explicitly disposed of by calling delete global reference. Index 21, and then it takes a global or local object reference, returns a global reference or null if the system runs out of memory. Delete global ref, obviously it just takes a JObject reference and delete it. Linkage this. Environment, global reference and global reference. Local references are valid for the duration of native method call. They are freed automatically after the native method returns. Each local reference costs some amount of Java virtual machine resource. Programmers need to make sure that native methods do not excessively allocate local references. Although local references are automatically freed after the native method returns to Java, excessive allocation of local references may cause the VM to run out of memory during the execution of a native method, right? Even for the local references, JVM has to create basically allocate some memory and resources. Delete local ref, it takes a local ref and then delete it. Parameters local ref, a local ref. Since so JDK 1.1 provides the delete local ref function above so that programmers can manually delete local references. For example, if native code iterates through a potentially large array of objects, and we've seen this in our discussion when we talked about object arrays, right? Working with primitive arrays is fine. Working with object arrays, we have to get it element by element, and whenever we say get object array element and passing the index, it creates a local reference and gives us a JObject, right? It's a JObject local reference. If the native code iterates through a potentially large array of objects and uses one element in each iteration, it is a good practice to delete the local reference to the no longer used array element before a new local reference is created in the next iteration. So when we're doing iterations and getting the object array element, it's good to, after each iteration, we manually delete that local reference. As of JDK 1.2, an additional set of functions are provided for local reference lifetime management. They are the 4 functions listed below. Ensure local capacity, JInt capacity. Ensures that at least a given number of local references can be created in the current thread. returns 0 on success, otherwise returns a negative number and throws an out of memory error. Before it enters a native method, the VM automatically ensures that at least 16 local references can be created. And this is what I mentioned before, that when we're dealing with local object references in a native method called inside the C++, the capacity is 16 and it doesn't automatically expand. So basically VM ensures that at least 16 local references can be created. So if we want to create 1000 local references, obviously JVM has some problem. So we can use this ensure local capacity and set it to 1000 so that we at least know that we can handle that kind of capacity. For backward compatibility, the VM allocates local references beyond the ensured capacity. So it actually can expand. As a debugging support, the VM may give the user warnings that too many local references are being created. In the JDK, the programmer can supply the -verbose JNI command line option to turn on these messages. So if you use -verbose JNI, it can print a debugging support for the native calls. The VM calls fatal error if no more local references can be created beyond the ensured capacity. Index 26 and then push local frame JINT capacity creates a new local reference frame in which at least a given number of local references can be created, returns 0 on success, a negative number, and a pending out of memory error on failure. Note that local references already created in the previous local frames are still valid in the current local frame. And index 19, pop local frame, JObject result pops off the current local reference frame, frees all the local references, and returns a local reference in the previous local reference frame for a given result object. Pass null as result if you do not need to return a reference to the previous frame. New local ref, we are manually creating a local ref, creates a new local reference that refers to the same object as ref. The given ref may be a global local reference, returns null if ref refers to null, right? Index 25. Weak global references. And again, this weak for making sure that there is no circular dependency. Weak global references are a special kind of global references. Unlike normal global references, a weak global reference allows the underlying Java object to be garbage collected. So again, if you're familiar with C++, smart pointers, shared pointers, you know that there is some sort of, when the circularity happens and when there's a circular dependency between the shared pointers, usually we have some sort of memory leak and we have to be very careful, and usually we use weak references or weak pointers to avoid that. So with weak global references, even if there is circular dependency, garbage collection can happen. Weak global references may be used in any situation where global local references are used. When the garbage collector runs, it frees the underlying object if the object is only referred to by weak references. A weak global reference pointing to a freed object is functionally equivalent to null. Programmers can detect whether a weak global reference points to a freed object by using isSameObject to compare the weak reference against null, right? If you want to check a weak reference is null, we can say isSameObject. Weak global references in JNI are a simplified version of the Java weak references available as part of the Java 2 platform API, java.lang.reflection API package and its classes. Clarification added June 2001. Since garbage collection may occur while native methods are running, objects referred to by weak global references can be freed at any time. While weak global references can be used where global references are used, it is generally inappropriate to do so as they may become functionally equivalent to null without notice. That's the indeterministic destruction, right? While isSameObject can be used to determine whether a weak global reference refers to a freed object, it does not prevent the object from being freed immediately thereafter. Consequently, programmers may not rely on this check to determine whether a weak global reference may be used as a non-null reference in any future JNI function call. To overcome this inherent limitation, it is recommended that a standard or a strong local or global reference to the same object B acquired using the JNI function new local ref or new global ref, and that this strong reference be used to access the intended object. These functions will return null if the object has been freed, and otherwise will return a strong reference, which will prevent the object from being freed. The new reference should be explicitly deleted with immediate access when immediate access to the object is no longer required, allowing the object to be freed. And again, this is the same situation we have in C++, in the modern C++ with smart pointers, weak pointers, shared pointers, and unique pointers. The weak, obviously in Java, we basically more or less have something similar to shared pointers, because we're just passing references around or passing pointers around. The weak global reference is weaker than other types of weak references, Java objects of the soft reference or weak reference classes. A weak global reference to a specific object will not become functionally equivalent to null until after soft reference or weak reference objects referring to that same specific object have had their references cleared. The weak global reference is weaker than Java's internal references to objects requiring finalization. A weak global reference will not become functionally equivalent to null until after the completion of the finalizer for the reference object is present. Obviously, finalizers have been deprecated since Java JDK 8, JDK 9, I guess. So, I mean, this might not be a valid statement since JDK 9, or whenever the finalizers are removed. They will eventually be removed from the Java. Interactions between weak global references and phantom references are undefined. In particular, implementations of a Java VM may or may not process weak global references after phantom references, and it may or may not be possible to use weak global references to hold on to the objects which are also referred to by phantom references objects. This undefined use of weak global references should be avoided. Okay, so I hope that's I think that's for this tutorial. Please stay tuned, and I'll see you in the next one.